Okay, number 3. At a certain instance, we have a particle-like object, and I don't know what the difference is between a particle-like object and a particle, but whatever. Okay, so this particle-like object is acted on by a force of this, which is given in vector form, while the object's velocity is this, which is also given in vector form. What is the instantaneous rate at which the force does work on the object? So we're going to calculate the rate at which the force does work on the object, and excuse me for leaving that up. So, cut. There we go. Thank you. All right. So, the instantaneous rate at which the force does work on an object. So, delta work. So, how much work you do in delta t. Well, the rate at which work is done is known as, you should recall, power. I got the power. Okay. And you can see the unit for power is watts. So that's why we have this thing. I apologize for the I got the power thing. I don't even remember who's saying that. Who's saying I got the power? Oh, was it CNC Music Factory? I don't know. Anyway, so before your time, I'm sure. So one of our equations for power, and the one that applies here, is power is if we have a vector force and a vector velocity, power is simply F dot V. Remember, this is the one we get out of MA dot V, and that's because and this works, and we remember from a long time ago that if we take the dot product of acceleration and velocity, that tells us whether we're speeding up or slowing down. If this product here, this A dot V, is positive, then we're speeding up. If it's negative, we're slowing down. Okay, so here we're just taking and multiplying by m. So if this is positive, then you're speeding up, which means you're gaining energy in the system. If this is slowing down, or if this is net less than 0, you're slowing down, which means you're losing energy. So this works exactly the same way. So now let's take our actual thing. So our force was 5I minus 3J plus 10K newtons. Okay, so this equals, there we go, equals 5I minus 3J, J hat, I hat, J hat, plus 10K hat newtons dot, and I think the other one was, let's see, negative 2 plus 4 K hat meters per second, okay, dot, so negative 2 I hat plus 4 K hat meters per second. So they were being sneaky on us by leaving out the J, so you got to watch out for that. Take this dot product, and taking a dot product is pretty easy. You just multiply components. So this dot product is going to equal 5 times negative 2, okay, plus negative 3 times 0, plus 10 times 4, which is going to equal, so this is negative 10, and this is 0, plus 40. So this is going to equal 30, and the rate for this is, well, this is Newton meters per second, which is going to be joules per second, which we know as watts. So 30 watts. Let us see if this is actually correct. 30 watts. And boom, yes it is. I am getting really lucky. At some other time, the velocity consists only of a J component. If the force is unchanged and the instantaneous power is negative 12 watts, what is the velocity of the object just then? So let's once again just apply our power equals force dot velocity, okay? And we know our force is unchanged. Let's see, the power was negative 12 watts. We know our force is unchanged, so this is going to be 5I hat minus 3J hat plus 10K hat. And we know that the velocity has only a J component, so we can call this speed in the J direction. And so we take this, this is V, this is just, our V vector is just speed in the J direction because it's only got a J component, we know. So when we take the dot product, I'm sorry, why did I put a plus there? That is so wrong. So that's actually a dot. I apologize for that. So dotted with VJ, okay. So we want negative 12, and so we take the dot product. Well, this term, so this 5I hat term and this 10K hat term are going to go away because there is no I or K component to the velocity now. This is just going to equal, so this then becomes very simple, which is negative 12 equals negative 3 times v. And so that just means v equals 4, and it's going to be meters per second, of course. So let us see if that works out well in the j-hat direction. Yes, it does. Okay, so that's how you do problems